All right, now that we've looked at ionic compounds pretty extensively, things that are made of cations and anions that attract and stick together once they do a little give and take of electrons to make each other benefit, it's time to look at another kind of compound, typically just made of nonmetals, either 2 or 3 or more different nonmetals bonded together. Okay, now we get a lot more options because instead of giving and taking electrons in covalent compounds, we share electrons. Otherwise, we end up with stuff that gets happier while something else gets less happy. Since the nonmetals are mostly over on the right side of the periodic table, we have a lot of things that are looking to gain electrons, not lose. So give and take is not going to be enough. Rather than that, they end up sharing electrons, so both atoms involved in a covalent bond, okay, will have ownership over the electrons in that bond. So everything ends up benefiting, and we don't end up with any ionic charges to keep them held together. They just hold together by that mutual benefit of sharing their electron clouds, by kind of overlapping them. Okay? So because there is no ionic charge here, we can make sharing of electrons happen in a lot of different ways for the same elements. So we have to be a little bit more specific with our naming to figure out how many atoms of each element are in that compound. So if you haven't already, make sure you watch Tyler DeWitt's video on naming covalent molecular compounds, because it's a great precursor to this. It covers a lot of great examples, and you might even find a couple that are straight off of this worksheet that are on there, so you'll get a couple freebies that way. Okay, so I'm going to do a couple examples on the first page, and then on the second page, I'll show you kind of what doesn't get covered in the video from Tyler DeWitt, where we are looking at a structure, a drawing of a covalent compound, and using that to figure some stuff out. Okay, so let's take a look at this here. So we've got the formula on the left side, which tells us how many atoms of each element are involved. Okay, and we've got the name on the right side that tells us how we put that in words. Okay, we've got our elements listed kind of left to right. So carbon comes first, chlorine comes second. So the roots of this are the same as with ionic naming. So we start with the first element rather than cation. So carbon stays carbon. The second element, in this case chlorine, becomes with an IDE ending, chloride. Okay, but again, we need to be more specific about how many atoms there are of each element. So in order to account for this 4 here, I need something in the name to tell me there are 4 of those chlorine atoms, which is what this tetra is here for. All the prefixes you will need are down here. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Okay, so let's try those out on a couple of these examples. And we'll talk about some of the kind of weirder things that can make these a little bit tougher. Okay, let's start with this guy right here. We've got Cl as our first element, and we've got O as our second element. So my name is going to start with chlorine. Chlorine. My second part is going to be oxygen with an IDE ending. So oxygen becomes oxide. Okay. But instead of just calling this chlorine oxide, I need prefixes on there to say how many atoms of chlorine and how many atoms of oxygen there are. Okay. In this case, I have 2 atoms of chlorine. So if I go and find my prefix for 2, that is di. So this is going to be dichlorine. All right. And I'm going to need more space for the second part, I think. Oxide, kind of squeeze it over here. Okay. The prefix for 7 for my oxygen is hepta. Okay. So I precede that oxide part with hepta to say that there are 7 oxygens there. So the name for this right now looks like dichlorine heptaoxide, which is not bad. This heptaoxide part is a little clunky with the A and the O next to each other. So it would be best if we kind of fix this up a little bit. Okay, and the way we do this is if you see an AO or an OO, we change it to just O. Okay, so I'm going to drop that A. Instead of heptaoxide, it's just going to be heptoxide. All one word. Let me scooch this a little bit closer. Heptoxide. Okay, so the name of this compound, Cl2O7, is dichlorine heptoxide. It's made of only nonmetals that are sharing electrons rather than doing a give and take. Okay, let's do another one. Do number 3, where I just have 1 atom of carbon and 1 atom of oxygen. Okay, so the base of this name is going to be carbon for my first element, and oxygen becomes oxide for the second part. All right, then I look at my prefixes, and since there's just 1 C here and just 1 O here, I need a prefix for 1, which would be mono. So your first instinct would be to do monocarbon, monooxygen. Zoomed in a little bit. Okay, and that would seem to make quite a bit of sense. But for some reason, we don't use mono on the first element. I guess we just figure it's kind of implied if we don't say it. Okay, so if you'll notice up here, we also had 1 carbon in CCl4, which we called carbon tetrachloride. We didn't call it monocarbon tetrachloride, we just called it carbon tetrachloride. So somewhere down the line, historically, we just decided, we don't need mono for the first element. We're just going to imply it if there's no prefix. So instead of calling this monocarbon monooxide, it's just going to be carbon monooxide. Mono for 1, oxide for oxygen. Now carbon just stays like that with no mono prefix. Okay. Now, just like with the heptaoxide becoming heptoxide, you might notice this monooxide is kind of clunky. So to make this sound a little smoother, we're just going to change that to monoxide. So carbon monoxide is the name for this formula here. Again, another covalent compound made of only nonmetals. And you probably recognize this, carbon monoxide as something you hear in your day-to-day life. Okay, now we can also go the other direction. Okay, so let's say I've got this, let's do phosphorus pentabromide. We'll do this last one. Okay, well, I've got 2 elements here. Phosphorus is the first one, and bromine is the second one here. Okay, if I go look up on the periodic table what each of these are, phosphorus is P, and bromine, which got changed into bromide, is Br. All right, this penta prefix implies that there are 5 of these bromines. Okay, and I don't see a prefix on the phosphorus, which is implying that there's 1. It'd be like if we put mono there, but we decided it just does not go on the first element for whatever reason. So this compound would have a formula of P1Br5. And a lot of times we also imply the 1 in general in formulas too, so this ends up going away also, funnily enough. So this is going to be written out as P, and again we drop the 1. It's not technically wrong if you write it, but it's kind of a fashion faux pas in chemistry. So PBr, then 5. So phosphorus pentabromide has the formula PBr5. Okay, now let's see how we can do this with the structure of a compound. Okay, when you see a drawing like this, these lines here are your covalent bonds. When we had ionic compounds, we would have a cation in brackets with a little positive charge up in the top right. We'd have an anion also in brackets. Usually would wind up with 8 valence electrons, and it's got a little negative charge in the top right. And then they attract to each other because of that positive and negative charge. Okay, in this case, we use a pair of electrons shared between two atoms, kind of showed as a line. So let's see here. So oxygen usually starts with 6 valence electrons, and each of these fluorines would usually start with 7. 1, 2, 3, 4, 5, 6, 7. And what this line stands for is there's a pair of electrons, one from one atom, one from another, that's being shared between these two atoms. So both atoms will have ownership over that pair of electrons. Okay. Now, for now, the way that the bonds are drawn out and the way that the atoms connect is not going to affect our formula or our name. All we really need to know is how many atoms of each element are there and how we put that into a name. Okay. Typically, we'll end up putting the kind of middle element first in the name. Okay, or otherwise we just read it left to right. Okay, so in the case of this guy here, we put oxygen first just because it's in the middle. It's kind of the odd one out. Okay, in the next one, we'll put hydrogen first because it's on the left side. We're just going to read it left to right. Okay, so in this first example, oxygen comes first, fluorine comes second. Okay, and again, the only thing that count is how many atoms of each element there are. So in this case, we have 2 fluorines, which is why we have this 2 here. And we have 1 oxygen, which we have kind of implied down here. Okay, so OF2 is our formula for this compound just by counting the number of atoms of each thing. We have 1 O, we have 2 Fs. I don't care about how many electrons, how many dots they're showing, or how many bonds there are, and what bonds to what. I'm just taking an inventory of what atoms are there. 1 oxygen, 2 fluorines, OF2. Okay, then I can change that into a name. Since there's just 1 oxygen, it could be monooxygen, except we drop the mono for the first element, so it's just oxygen. Okay, since there's 2 fluorines, the prefix is di, and fluorine becomes fluoride. Difluoride. Something like that. Okay, if we look at the next one, we've got hydrogen on the left side, so we'll just do that as our first element. And iodine is our second element over here. Okay. Now again, I don't care how many valence electrons each of them, have and what they end with for now. In order to figure out the formula in the name, I just need to worry about how many atoms of each thing there are. Okay. There is 1 H right here. Just 1 H. So I'm just going to write H. Maybe I'll just give myself a little note that there's a 1 there, but I'm going to leave it out in the end because it's implied. There is 1 atom of iodine. So this would just be I. Oops. And there's just 1 of them. Okay. I'm going to erase those ones because I don't really need them. Hi. So now, when I change this into a name, hydrogen stays hydrogen, and if it had to have a prefix other than mono, I would write that. Okay, so like if there are 2 of them, I would write dihydrogen. If there are 5 of them, I'd write pentahydrogen. If there are 8, I would write octahydrogen. But I don't. I have 1. So we're going to leave the mono out for the first element. Okay. The second element is iodine, which becomes iodide, just like we would do for an ionic compound. And its prefix is also going to be mono for one, but we can use it on the second element. So this is going to be monoiodide. Okay. Now you also might look at this and be like, "Ooh, that sounds a little clunky," but it's not as bad as the AO or OO, something like heptoxide or monooxide. So monoiodide kind of gets away with it. Oxides are the big guys you have to kind of worry about with prefixes, and everything else kind of gets a pass. So monoiodide is going to look weird. It's going to sound weird, but surprisingly, it's one of the ones that gets a check mark for us. It's got an A-OK. We just leave it as monoiodide. Okay, so for the rest of these, look at what atom is either in the middle or on the left. Okay, in this case, we've all got atoms in the middle. So those are always going to be what starts your compound. Okay, it's going to be the first element in your formula, and it's going to be the first element in your name. Okay, don't forget to change the second element's name to have an IDE ending, and use your prefixes to say how many elements or atoms of each element there are, like 1B and 3Fs. Okay, and don't forget the first element does not get the mono prefix. Only the second one can get the mono prefix.